So, welcome. This is the second demonstration that we are having. This is wire arc implemented. So, yesterday what you learned was wire laser implemented. So, I'll just begin with a brief discussion what Prachi discussed yesterday. I'll just reiterate that. So, you guys remember that last time, yesterday, she discussed something about DED. Do you know the full form of DED? Directed energy deposition. Directed energy deposition. So directed energy deposition means you are directing an energy to a particular point, and at that point you are basically also depositing, you are also feeding the material, and because of the need of that energy source, that material melts and it is getting deposited, which is also the basic of welding, right? Depending upon the heat source or the energy source that you are using, you can use an electron beam, you can use a laser source, or you can use an arc. Okay? So, when you are using an arc and you are using wire, metal wire, as the feeding material which you want to deposit, that becomes a wire arc and then additive manufacturing. That much is clear. So now, there are many companies who are basically providing their facilities or building plots, right, for this arc manufacturing. So the machine that we are working today is with wire arc manufacturing is Ponies. Okay, so Ponies is a well-known company. Okay, and the configuration of the machine that we are using today is CMT. So what do you mean by CMT? CMT is cold metal transfer. What does it mean? What do you think it means? Metal transfer is clear. Now a word cold has come. What does it mean? Not room temperature. Yeah, okay. I mean, see, any kind of work that you are doing, welding and all those things are happening at an ambient temperature only, right? The surroundings are ambient only. That is a given consideration. When you say cold, what do you mean? Something to do with temperature, right? Something to do with temperature. Now you guys have seen welding or not? Sometime or other you might have seen welding now. So when you are using the CMT technology, what happens is, see, when you are feeding a material, for example, this material is coming, okay, and an energy source is also coming, okay. So in other welding machines, the material will keep on coming continuously in the forward direction. The material will, the wire will be fed in the forward direction, okay, from the torch, it comes and it keeps on feeding in this direction and it keeps on depositing. Understandable? In CMT, they have developed a technology that it is a rotating mechanism kind of thing. So, material just touches, creates spark, retracts, touches, retracts, and that happens quite rapidly. Okay? So, for very small amount of time, the material is in close vicinity with that arc regions, right? Excited region, so that the arc is quickly created and distributed. You understand? When you are doing that, material is not being fed at all times, right? It is coming and retracting. That means only for that amount of time when the arc is generated, for that small time, only that time the heat is generated. It is not a continuous kind of thing, right? Heat generated, heat gone, generated gone. Okay? I mean, the heat is very much controlled. The energy that you are putting is very much controlled. It is quite intrinsic to that particular time when it is touching and creating an arc. After that, there will be no. So, because of this, what will happen? The total amount of heat input that you are giving is reduced. Because of that, what will happen? What can happen? So, did you attend yesterday's class? They were discussing about columnar blades and iliac strains, right? So, because this arc process, any arc process, right, takes a lot of energy, lot of heat, right? So, its cooling is also very quick. RAM, any additive manufacturing process, any metal additive manufacturing process has very high thermal cycles. Okay? So, high cooling, high heating, high cooling, high heating with every layer. You understand? So, because of that, what will happen? A columnar kind of grain structure will evolve in the direction of blade. Okay, so for example, just बॉल लेके आ लो, डिपॉजिट ऊपर ऊपर इधर टेबल पे, हाँ वो वाला, this is the mild stage. Okay. So this is one layer, then goes up, second layer goes up, third layer goes up and down. Okay. So as you are doing, this is the build direction, and this is the deposition direction. You understand? This is the deposition direction, and this is the component in which direction the component is being, right? So as if you are using too much heat, all this microstructure will come like this and come in the this columnar rays will go in the z direction. This is known as epiaxial flow. Okay, and this is the basic reason for anisotropy. Now do you understand? When we were discussing yesterday anisotropy, why are additively manufactured components anisotropy? Because they have different properties in different directions. Why? Because of the direction in which the grain is going. And another thing, second thing, the difference in the grain size. Right? So in the center, because the heat in the center of this component, in this whole wall, the central grain, the grain is coming like this. Okay, this is known as grain. In the center, the grains are very big. And as you are moving towards this direction, okay, the grains are coming from equiaxis to columnar. Okay. Another thing that is there is, see, when you begin deposition on this substrate, see, substrate is a metal substrate. Okay, this is an SS substrate. Okay, SS base plate, what you can say, substrate or base plate. When you are depositing near to this, the major mode of cooling is conduction. But when you are moving to this region, right, maybe the heat is coming up, this layer is being deposited and heat is coming up to maybe this region, right? So then major contribution of cooling is
both.
Conduction little bit, but convection will be major because now it is surrounded by ambient atmosphere. But the region which is in contact with this upper layer is very less. When it was depositing near to the substrate, the region of contact was very big. It could have been distributed to a larger extent. So here conduction will be the major component, convection will be the minimum one. And of course there are radiation also. But when you are going to the top layer, then convection will be the major source and conduction will be the smaller source of cooling. So because of this cooling mode change also, the grains will be different in different regions. And so the properties will also be different in different regions. Why? Here cooling will be just learn for a method, or there is a thumb rule. If the cooling is quicker, then the grains will be smaller. If the cooling is slower, grains will be smaller. No, cooling is faster, then grains will be smaller. If cooling is slower, grains will be bigger. Simple? Okay? So here in this region, the grains will be, the grain size will be small. So when grain size is small, what will happen? Hardness will decrease. Microstructural, this grain size will also be almost equiaxis. But when you are moving up, now grain sizes are big. So if grain size is big, the properties will change. Yeah? And that is happening in the z direction. Grain is changing in the z direction. That is why that much is easy. That much you understood. So today we are working with GiAN. Why are we doing? We are using mass as a source to deposit wire. Okay, this is a mild component which has been deposited with this machine only. Mild steel GiAN 17 is the board that we use specifically for here. ERB is electrode or rod. Okay, the material is in the form of electrode or rod. Then 70 is the tensile strength in ASI. Okay, and then S6 is the series, big series. So that depends upon the alloy elements, right? Okay, so there can be manganese, there can be silicon, whatever is big in that everything. How is that fair to do? So please come.
Can the substrate be treated at a particular place?
Yes, possible. See, I tell you, when you are working with that kind of efficiency, let's go with IC. I'll go with a very simple example. Melting point of IC is the melting point. 1638 to 1670. That okay. Now, if like such as stated, can you maintain the substrate temperature? So you can maintain a range of temperature to a specific point to not. Okay. Now, how is that possible? I'll tell you that. What you do is beneath this substrate layer, you can create another substrate, another rock in which you can pass the coolant. Coolant liquid can be passed through. Okay. So that can take the heat from this substrate. Possible. Okay. But you can only get a particular range. You can just get a particular point. Okay. That range of temperature can be maintained subject to the flow of the coolant. Okay. There should be no obstruction. Depending upon the path the coolant is following. Okay. That will also affect us. If I am just taking two paths of coolant, it goes like this, comes like this, and goes like this. The heat flow will be less. But if there are 100 points of coolant movement, it will be more uniform, right? I hope it anything else? Go ahead, ask.
Towards the substrate, the material is brittle, and towards the non-rigidity, little enzymes or
You are talking about this part. Yeah. So okay. What I'm saying is this: yes, when you are near the substrate, right? Of course, the grain size will be less, hardness increases. Yes, but there will always be a yes. There is always a chance of, I will not say brittle. It will be less than grain. See, when you say brittle, that is whole different kind of material. You will say it will have less conductivity, more hardness, condition will be more efficient. Yes, hardness is more, grain size is less, hardness is more towards the brittle side, but not. Okay, and that can also be reversed. See, that can also be reversed out by doing heat. Once you have taken this, just take this part and cut it from here. I'll go and elevate. Stress relieving happens. Okay, so you can do that. Stress relieving can happen. Okay, so whatever its melting point is, of that, you keep at that temperature for 2 hours. This is all the stresses are there. Okay, but this is not stress relieving to be actually not. Stress relieving again doesn't change. If you go beyond its recrystallization temperature, then beyond. So there are several kinds of annealing. If you are using this below recrystallization temperature or warm annealing, what we call as warm annealing, what is that? That is basically to keep it at a slightly higher temperature but below the recrystallization temperature. Because all this is because of the rapid heating and cooling down, right? So there are thermal stresses in this, right? Okay. So you can do that. The stresses will be relieved. Okay. Now if I check this in HRD, it will give me a compressive residual stress. The stresses will be compressive in nature. Okay. But once I do annealing, stress relief, this will become going to tensile. Okay. Okay. Fine. Yeah, it will change. Yes. And now, see, two things. One thing is the main size is the direction of weight. Two different things. If you are going beyond the recrystallization temperature, yes, grain size will change, but the direction of it that one. For that you have to go to higher temperature. that direction of whatever direction you want, possible. That is also possible. But then you have to kind of external like loading kind of do some processing at high temperature. So that is what high temperature function. You are trying to get a grain orientation in a particular direction. Right? That also happens. It's possible. But just you go this way that but there is this. Okay? And yes, of course, one more thing. Like is mentioned. So when you are doing alignment, how fast you are coming like alignment which you are going around 600 for example. Okay? And then how fast you come to move temperature. That will actually control the frequency. If you move down very quickly, smaller frequencies. If you are going slow, 2-3x kind of thing. But bigger than the fast. You know the difference between quenching and all this? Okay. That is what we're saying. You are not using the cooling substrate. Maybe 10 years from this substrate, rays are purified and then another kind of reaction happens. If you are using the cooling, maybe 50 years. Not more. Yes.
That's right. If you see the shape, it is slightly curved. That's what I what do you think?
So what happens is it is basically higher at this region and bulging at this region. This is because of the printing strategy that I have used. Okay. So if you are using the same unidirectional direction, like it begins from here and goes till there, okay, then this side will start to fall down. I tell you why. So what I have done is first layer if I go like this, second layer I go like this. So this is by taking an assumption that uniform heat distribution happens. Okay? So because when you are ending the arc process at a particular point, okay, or you are beginning at a particular point, the energy will be more than what is usually at the other regions. At the starting and the ending point, the energies will be different, which are just very used. Okay? So if you are using this as a starting point, okay, so this bulge will be bigger. Okay? And then you are moving to this direction and you are here you are stopping it. Okay? So when you are stopping it at this region, so this will keep on bulging and it starts to bulge in this direction. It starts to fall. Okay? So to avoid that, create a like a common shape. So we are going with this kind of shape. Now, what is asking? Why is it this region at the like a higher, little bit higher and then this is why? Because whenever we are conducting deposition, we have to take a safe distance between the VAM rods and this substrate. See, this was the bead. I want to deposit on top of this bead. Understand? Okay. So the welding rods, I have to keep a certain distance. That is known as the set of distance. Okay. So that set of distance are basically taken at the center. So when you are taking at the center, you are basically, for example, now from bead itself, it is coming like this. See, bead will never be having equal kind of geometry. Aspect ratio, it will never, okay? So if I am taking at the center, it will basically keep on increasing from the center. That is also, but when we are using a cumulative effect, you will see a little bit higher percentage. Yeah? So this was just for design. If I am taken at this point, this would have a higher. If I am taken at this point, this would have a higher. Okay? Fine? Can we proceed? You can ask questions about the
कल
And deposition part will take care of later. Okay. Because we have one more training BMC, then I will take care of that. I will show you. Okay. So this is a ABB robot set. So this is known as a robotic arm. Okay. Robotic arm. Robotic arm is somewhat equivalent. Its mechanism is somewhat equivalent to our arm. Okay. So this is your base. Okay. On this base, your robot has been mounted. This has been mounted firmly and it does not move. But if you have to make larger components, because additive manufacturing is now making larger components, you can put all of this structure onto a rail kind of system, conveyor kind of system. And to lengths you can conduct deposition, doesn't matter. Okay. So now it is fixed. This is your fixed plate, and then these are the joints. Okay. So this is the first. It rotates. Okay. Then this one, second. Then third, fourth, fifth, and sixth. Okay, 6 joints. 6 joints means it can move in 6 different directions. So this is 6 degree of freedom. I think you know the concept of degree of freedom. Even if you don't know, then it is basically what kind of mechanism you can use to make a motion in a particular direction or a particular way. Okay, so this rotates. This can rotate like this, 1, this or this, 2, okay, 3, 4, 5, and 6 rotation. Okay, so this is a 6 degree of freedom motion. On top of it, we have installed a WAM CMT. So this is known as the WAM kind of setup. This is 4S CMT. The material is coming from this. Do you see this spherical casing? Yeah, so material has been mounted in this, okay? And then the material is being fed and it is coming through this to this. Basic thing, just what we do in welding, that is the basic. So, what do we do in this is, we will basically create a program, okay? For example, any kind of component that you want to fabricate. So we have to first take the design of that. So let us go back to the slicing part. Do you remember? So any component that you can think of, you have to basically create its design. Once you created the design, then you will conduct its slicing. And its slicing will then be created into a G-code. So that G-code, similar G-code works in this way. Understand? G-code specifically means how your component will move in X, Y, and Z. Basic. Okay? Let us not get into the intricacies of it. So what we do generally is in this kind of component, there is 2 kinds of coordinates that are, because this is a robot, that is why I am explaining it. In other machines, it is not the case. But in this case, because major thing is the robot, let us discuss. 2 kinds of coordinates are there. One is the world coordinate, one is the tool coordinate. Okay? World coordinate is something here. So the whole environment of this robot, okay, is centered at this position. At the center of this, there is an X, Y, Z. Okay, that defines the coordinate of this robot. Why is that needed? See, do you see this space? Right? If this robot doesn't know where its whole machine's X, Y, Z 0 is, then it will not know where to move. As in, for example, if it thinks that its coordinate is not here but here, okay, then it is programming and it can basically strike with this. Okay. So to define a coordinate of the whole setup, the world coordinates are put in this. They are standard, they are calibrated once in a lifetime, and then you don't need to calibrate it. Okay? While installing, only they calibrate. Second thing is the tool center point or tool coordinates. So anything you put on this robot, see, this is known as the end effector in terms of robotic terms. See, now we are talking about welding or something. But say, I don't want this welding. I want a pick and place kind of tool. I want a gripper, jumps, picks, places it. So I can remove this and I can put a gripper kind of. Okay. So how do I remove this? I remove this, and this is known as the end effector. Okay. This is known as the end effector. Okay. So the tool center point, any tool that you are using, okay, see, this tool is different, this gripper will be different, gluing mechanism will be different, right? Marking system will be different, okay? So, you have to have a common coordinates at the end of this robot, because this is the 6th axis, this is the 6th axis. And you should know, the robot should know that now I should have a single coordinate which can take care of all these things, right? Any tool you put, it can take care of that. So, a tool center point has been defined on this, on the top of this. Okay, again XYZ. Okay, and then that XYZ, so this is X for this robot, the X motion from here is this, Y is this, and Z is this. Okay, positive, negative. Okay, you change this, you put a gripper, you put anything, this will know, this point will know. Okay, you don't have to manipulate. And then on top of this we have put a WAM torch, okay, and then there is a tool point which is at this. There are two things. One is the tool center point and then there is the tool coordinate. Tool center point is this and it is irrespective of any tool that you are putting. But specific to this tool, a tool coordinate has been put on the tip of it. How do you define this? You basically take, like for example, consider 0.1 only. Okay, by 0.1 we are increasing the distance, and then we are again trying to take out the paper. Once that paper is fixed, it is stuck. At that time we know that this has achieved the zero distance, and then we know that it has basically crashed. But that motion 0.1 mm, by 0.1 mm we can continue. Even more than that, 0.01 also, 0.001. That is possible, and we do that. Okay, so by that the zero coordinate is measured, and then we take the robot, and then whatever programming we have done, we will conduct the demonstration. I think your answer is also there in this one.
So this is the similar like we are doing in the CFC.
Same thing. Yeah. See, any computer controlled thing will have the same thing only. The terms will be different.
But there we have those probes where we dimension probes. That is more difficult. Because there the tool is starting from that point. There is a very towards
So whenever, now this question is fine. When I am saying that we are touching the component, there generally CNC machines, we are going for some machining or some kind of a tool is there, and we want the zero for that. Okay? Here also we want this to touch this, and then after that we will keep a safe distance that has to be kept so that this doesn't strike. For this machine it was 6 mm. For this machine we used 5, 10, 11, 12, I have used 15 also we have used, depending upon the component. Right? So yeah, that is this. But see, you have to keep it a little bit up, then the 0 point, you have to keep a little bit up. Always we do define, when I will be discussing that VMC with you, then I tell, I also go to this point, I touch it, but after that I will take 11 mm up, so that it doesn't strike. And that is known as the standoff distance.
The standoff distance is equal to this arc length.
No, standoff distance is different. Arc length is different. Totally different. Yeah. So okay. So whenever okay, I will discuss 3 cases. One is the vertical tool, 90 degree. One, consider the deposition is happening from here to here. One is vertical, going like this. Okay, going like this. When the heat source is like this, the heat will be dissipated in what direction? Vertically downwards. Major dissipation. The first dissipation will be downwards, and of course it is a 3D kind of thing, but it will go like this. When it is a advancing kind of thing, basically the angle is like this, heat source will be that way. If it is a retracting kind of thing, heat source will be different. Correct? Depending upon the angle and of course upon the material feeding. See, if material is being fed like this, so you are moving fast and material is going back, the heat which is being deposited will be different. If you're going like this, different. If you're going like this, depositing like this, things will be different.
Can the speed of deposition be varied?
Speed?
Speed of deposition be varied?
Yes.
So how do you calculate the SOD?
Experimenting, trial and error. So if we are keeping too close, the standard distance is too close, the material will flow. Because there is a very small distance, na? Heat is concentrated in a small region. Material flows like this. Bigger beads you will get. And if you are keeping too high standoff distance, the beads will be very narrow. Porosities can also be there. So that we have to do. Trial and error.
That parameter is also considered.
Yes, we do that. That is an important parameter. When we do optimization studies, we have to conduct optimization studies. Basically, we use current, speed, and standoff distance. Mostly.
Is there any prediction between the deposit and material and the substrate? Do they have to be same or
No.
can it be different?
It should be compatible. Like for example, stainless steel on copper, not possible.
Copper on nickel?
Not possible. I mean possible, but the problem is it will form intermetallics. It will just break away like that.
So here you have
It will be quite
picture is substrate and material.
This is aluminum, this is aluminum.
What about this question?
This is different. This is work table. Any material can be there, work table remains there.
So for the optimization, which parameter?
As I told, standoff distance, current, speed, torque speed, and then we also use gas flow. If you want to do angle also.
Nozzle is same? Nozzle.
And the output you measure is like
Bead geometry, bead quality. Copper nozzle tip. Nozzle tip is copper. Contact tip is not copper. And this is brass. So not on this. Not on this. Experiments will be run on the VMC. I have installed similar machine there. It will do.
Which is the major challenge during this
Major
uncontrollable factor
uncontrollable factor.
which affects significantly.
Atmosphere.
Atmosphere.
That is not. If I am depositing now, that is a very good question. Why is this robot and this laser-based system placed here where there is an AC and this is a closed chamber? Whenever we are conducting deposition, we switch on the AC and we create a temperature zone and then we will it gives consistency. But in real life, when you go outside, no ACs are available. So if the quality of the part deposited in Alaska, America, and India will be different. And that is why when we are conducting optimization studies, you will find 20 or hundreds of optimization studies. But optimization study can never be a globally accepted optimization. It can never be. It is always best for your local. That is true. That is something that is a necessary evil to find. Even if you just take a paper and replicate everything, not possible. What will you do after humidity? Hundreds of things will come. What will you do? If a machine is brand new, it is working differently. If a machine, same ABB robot, 15 years old, it moves with some jerks, part quality will be different. What will you do? So that is uncontrollable. Other things are controllable to some extent. Comparable things you can do. We do now. That is what we do. So we have displayed the posters actually in our lab. Once you visit our lab and then you will see. We have installed a lot of posters. We have done everything. Now we are conducting post-processing, that kind of things. Okay? Understand? Yeah. So that much is it. So we'll basically bring the torch here, we'll conduct the deposition. That is what the whole kind of is. Yeah? Okay. Okay. So minimum wire diameter that we can use in this is, or for any metal, is 0.8 mm. Maximum 1.6 mm. Comes in 4 0.8, 1 mm, 1.2 mm, 1.6 mm. Standard wire diameters. And because after that it will just become a rod only. Then TIG welding will continue. Any other question? Depends upon the material. It depends upon the material. So he's asking about the shielding gas. Yes, whenever we are using arc or laser or any kind of heat source, yes, we have to shield that. Okay, that shielding is done basically to protect it from the ambient atmosphere. That is done with the help of a gas. Mostly we use noble gases. Okay, so argon is there, carbon dioxide is there. Both are there. Both, depending upon the material. Yeah. Any other question? No. This is aluminium.
So how you remove that part from it?
Take the substrate, cut the piece.
Only to remove
Viridium is there. Viridium is there. And then if you want to go, you can go with a blade, this blade saw, hand saw. That is also possible. And for fine component, you have to use viridium.
axis. That is the limitation.
Okay, yeah. So from conventional printing processes, you have 3 axes only, X, Y, Z. This has 6 axes. So design freedom is there.
3 translation, 3 rotation.
Yeah, those type, no, that, I mean, from a general chamber-based 3D printer, they're asking how is it different? So, additional 3 axes. Any questions? No? Or you will come later. Okay, I think that is it. I explain in a very simple way. I want to print a component from here to here. How do I know the starting point? I need this to this point. This point, machine doesn't know this coordinate because this is a this much substrate. If I am using this much substrate, robot doesn't know what is there, what is in this. This can be this much substrate also, right? Anything can be there. This can be anything, right? The robot doesn't know. How will robot know? Related to this, the position of this, the robot will know. Because specifically, it is not even this position. This position is a reference for us. The robot only understands this position, which is the tool coordinate. Yeah, that is always fed to the Oh, that is different. What that was, that is different. That is a set of that I tell. That is okay, what he's saying is okay. So this tool, I tell you, this tool, specific tool, okay, this is pre-programmed in the software, whatever software they have in the Robot Studio. They are already pre-programmed this, and this is a very standard kind of thing. And the installation has also been made like that. And whenever you use clippers or painting mechanisms or something like that, those are very standard dimensions. It is not that I can make something and I can put it. If I need to put, then I have to define all the dimensions. I have to put all the design. This whole design has to be done. So the distance between this and this is basically, then I have to calibrate and put. But for this machine or for any standard machine, these are already pre-installed. This much is it. So the machine comes to this point. Okay. this is my reference that I want this tip to come to this because I want to print begin printing from here to here. This is my reference. What is the machine taking? Machine is taking this. So here the coordinates come to this point. Now I know that I have to come, whenever I have to print, I have to come to this point. So this is the circular part. The circular part knows I have to come to this much. And then I have to move like this. It doesn't care what tool is there. Even if it is a painting tool, it doesn't. Okay? Do you understand? If there was a painting tool this much size, so then it would have come a bit closer. Of course, then this, see this is this much length. 2 arms, 2 hand length. Consider this much is the tool. It will come closer. This thing will also come closer. So it is only taking care of this coordinate. And this is our reference. Do you understand?
1 second. 1.5. 0.5.
It is not linear. No, I tell you. So I tell you, that is good question. So forget about this. Any tool, okay? This component is coming to a particular distance because of this tool, because of this length. It is coming forward. For example, this circular thing came here. Now it is having some coordinate, local coordinates of x, y, and z. Z is this position. Okay, I have this position, and this table is already defined. Okay, this coordinate is also being taken with reference to this, which is always fixed. Do you understand? The distance of this from this is always being taken care, because this is a fixed thing. This can always change, right? So wherever it comes, a relative distance of 6 degrees of 6 coordinates is being captured from relative to this. So this has been made 0, 0, 0, 0, 0, 0, 6 coordinates, and relative to that, its x position, y, z, 3 rotations in x, y, and z. That is being taken care of. So irrespective of this rule, this will take care of.
I think it is there's no flashing over the screen.
Sorry.
The upper part, it takes
This
care
one?
of, yeah, it takes care of it to not smashing over.
No, that is not the case. That we have to take care.
That's
See, that smashing, that is what he was saying standoff distance. He was mentioning something 6 mm. That is the safe distance that we have to keep from this to prevent it from smashing. For this material, it is 6 mm. And why 6 mm for this? Why did she specifically mention 6 mm and I am not mentioning anything for this? Why? The answer is in energy source. Good? Very good. So, the answer lies in the laser source. So, you have to have a collimated laser source that has been calibrated at 6 mm distance. Any substrate 6 mm above it, the laser properly collimates and gets pointed at the center. That is why 6 mm. Here we can use anything. Any distance. I use 11 mm. I have used 11. I have used 6 also. You can use anything. Depends upon your optimization process. This is understood. Any questions, please? Let us go into the 12th standard. Cathode and anode coming close. What happens in between the air? How? It is a closed system. See, cathode, anode, and one more thing has to be there. Cathode, anode, and no. Medium can be air also, vacuum also, water also, anything.
current passing
How does that current pass?
from cathode and from cathode.
Because it has to be closed system. Until it is not a closed system, the current can never flow. That much we know. It has to be a closed system. That much we know. So that closed system is done with the help of an earthing, and that is also a safety source. You used to see when you used to make that electric diagrams, there used to be a switch now. If you open that switch, current is not flowing. What is that switch? Either it can be that switch, simple switch, or that will also make a closed system. What is a closed system? Basically, current should flow. Either that can be a switch or an earthing system. That much is clear? Okay. So, whenever you are bringing these two things close enough, and that is the principle taught I am explaining about the art. when you are bringing it close together, what is happening? It is a closed system. What is happening between the air? Yes, the electrons are, that region is ionized. Okay, and what starts to happen? The flow will happen from where to where? And if that flow is quite high, what will happen? Spark. Why?
Because there is very less distance.
And that is known as the standoff distance, which you were talking about, 6 mm. You understand? So there will be a minimum distance beyond which the ionization will be so much high that it crosses the. There is a word. Come on here. Well standard. It crosses the threshold. And when the threshold is crossed, what happens? A spark is generated. What is moving electrons? Basic terms we are speaking. So that becomes so much ionized that it basically takes a form of an arc. And that arc has so much temperature that whatever material is coming, that basically melts because easy. Understand? Basic things only, no? 12th standard thing only. Okay, so now we know why they taught us that. Yeah. Okay? See, this much is it for the robotic part. Now we'll move forward. Any questions? Sorry? Cost of this robot?
That was 3 CR.
Some crore.
In crores.
In crores.
But I don't know the specific. We are not good with the specific. But in crores.
Which materials in this, which materials in that?
Sorry?
I mean, what is the material segregation for arc and laser?
I don't understand the question.
The material should be specific to that particular tool which we are using. So any material,
Any material that can melt.
But in laser, some specific material there.
No. Laser
Like
cannot.
aluminum is not possible.
Aluminium is not there in this machine. Okay.
For our machine only.
Okay. Yeah. We should be very specific. Aluminium is not possible in this machine. But if
Why?
because which kind of laser is it?
Blue or red? Red or blue?
Blue laser is coming now. So when blue laser comes, and another thing is because aluminium is very
Effective.
no metal. Another thing.
Reflective.
Refractive.
Refractive. So then what will happen? Laser cannot basically. You understand? But with arc it is possible.
For laser, if you make some shielding purpose, like some extra chamber like this, then it is
When it is
possible.
possible.
Its
In
cost
fact,
is more.
this material is aluminium. She don't need to do. This is aluminium. She has carved out the substrate and taken it. But yeah, this is aluminium. Aluminium is possible. Okay? Any more questions? You can print gold also. You know that? Maybe we should print some ornaments also. Yeah. Any questions, please? Then we'll ask
which
her.
material should go for arc and which material should go for laser.
Any
I mean,
material.
there are two different.
Heat source.
Yeah. So how do we decide which to go for this and which to go for?
Like,
Why do you have two machines for?
yeah, before purchase the machine, there are some specification list, which material some specific of that laser machine, and which material is specified for depositing that machine. So that this aluminum is not possible in laser, so that we purchase one piece for aluminum only.
I'll add something to that. See, laser and arc, irrespective of the machines that are available here, I'm just speaking facts. Both can print similar kind of materials. Now, why laser, why arc depends upon the heat source. Laser is a very concentrated kind of heat source. Arc is a very dissipative kind of heat source. Energy source. I should not say heat source. Heat source is something different. Energy source. Right? So the deposition strategy is different. The quality of the components is different. The capability of printing is different. For example, the minimum thickness with which this we can print is how much? 4 mm, maybe 3 mm. With this,
Laser is like
possible 0.5 mm also. Why?
That's upon our requirement, like your application, our requirement.
है ना? The materials. Okay, let me speak. This material, what we are using, the wire, the minimum size is 0.8 mm dia wire. Okay. Similar kind of material wire we can use here also. Okay. But here we can deposit the minimum thing from a 0.8 mm material. The minimum that we can deposit consider is 3. With that 0.8 we can deposit 1. Why? Because here the energy source is not concentrated, there the energy source is concentrated. It can specify to a very precise point. This can't.
For more precision, it's laser. Otherwise, it is.
Precision or maybe some kind of component. Like for example, you want a thin wall structure. Anything below 5 mm is thin wall. For us. For us. Yeah.
We look at different
Properties. Yes, of course. Cooling is different. Of course.
Energy source is different.
See, everything depends upon the heat source. Now, how it is cooling. This cools quickly. This doesn't cool quickly. This is faster than this one. So grains will be small. Grains will be bigger comparatively. More strength, less strength. Okay. Okay. Anything else? We can discuss.
The wire comes from Day, right? Which part of the robot helps to make the wire? How the wire is melted?
The wire moves like that.
Can I?
Robot is not helped made to make.
Yeah. Robot doesn't help to make.
So it's ours which is making the.
Yes. And to show that, because we are as of now, this robot is on some process. We are not changing those programs, so we are not conducting the position here. In your 8th demo that I am taking, that will be in VMC, same machine, I will show. We will deposit. Everybody will do it. Okay?
Yes.
Works? That day I will show how material is feeding and all the things I will show. For now, just material is coming from there. Okay? Any other questions? Take properly. Don't take photo change. And this is a review. See, so.
Function is pretty is cooling even or after. And that would be.
Heating cooling is very fast. Because it is metal now. Can we bring the other group? Yeah. If there are any questions, you can ask. Next group. Second group, sir. Please.
There is heated soap energy. I like laser on this R. This is R.
Please. Shafi sir, come sir. Your field only. Yes sir. Take their photos. I have much seen them. Come. Yes, sir. At least you guys should not be. Okay, everybody is here. Anybody outside? Should we begin? So again from the beginning, yeah. So yes, this is a robotic ABP robot arm on which the welding setup has been fixed, installed. Okay. So this is a 6-axis robot. Okay. So whenever you are saying the 6-axis robot means it has 6 different kinds of motions it can take care of, right? So consider that this is a fixed base. Okay. This is the first joint where it basically rotates. Second joint is this for this rotation. Third is this. Fourth is this. Fifth is this. Sixth is this. 6 degrees of freedom. 6 different motions you can have. Linear plus rotation. Okay. It is very equivalent to our arm, which can basically rotate, do this, move up, down, extend. Similar kind of setup. Understand? This much is okay. So this is the welding setup. Shown is CMT setup that has been basically installed on this. So the material is basically in that closed chamber. Okay, the material that has been installed is aluminum material. Okay, so that aluminum is basically being fed from all this path coming up to this point. At this point, the material is dispensed and deposited. Okay, so this is your substrate. Okay, and your tool basically comes here. Okay, and then it will create a standard distance, whatever standard distance, whatever safe distance you need. It will take that, and then it can conduct the deposition. Okay, so the basic behind that, before we discuss, there are two kinds of coordinates in this machine. Okay, one is the world coordinate, world coordinate. Okay, and then there is a TCP, tool center point. Two things are there. Okay, so the world coordinate is basically established here. World coordinate means this robot is wanting to understand the region like near it. Okay, so we are considering that this is the 0, 0, 0 of the machine, of the whole machine. Always you have to define, because based on this we will have a comparative kind of thing for other coordinates. So there has to be one fixed thing that doesn't change with position, with everything. Once this is kept, this is kept. Okay, so consider that this is the world coordinate of this machine. The whole machine is working relative to this. Anything 1, 2, 3, whatever motion it is taking care of, it is with respect to this. It is always a relative motion. Okay. And then there is a tool center point, TCP. See, this is the 5th joint. This is the 6th joint. 6th joint rotates. Okay. And then there is an end effector. This is called as the end effector. Okay. This is the end effector. Any kind of tool you want to put, you can put on this. Fine. Any kind of tool you want to put, you can put on this. So this is the welding torch. For example, I want to put a glue kind of system. I want to do gluing, or I want to put a gripper system, pick and place. Everything is possible, right? But irrespective of the tool that you are using, how does the machine know that what is the center point of this tool? So this is known as the tool center point. At this point, it basically defines the tools XYZ. Machines XYZ, tools XYZ. I should not say XYZ. Machine's position, tool's position. And then on top of it, you can put the tool. So for this machine, the X is in this way, Y is in this way, and Z is in this way. That much is clear. After that, there is one more thing known as the tool coordinates. So now when you want to conduct welding, for example, this is for my reference. Okay, I want to conduct welding. I want the tool to come here. For example, this is the tool. Tool comes here. Consider that this is the old tool that is coming. I want the tool to come here, and I want it to deposit. Right? So whenever it is coming like this, the tool center point is basically this tip. I want to know the position. For example, I want to begin the deposition from here, and I want to go up to this point, right? So I want basically to know what is the position of this tip, because material will come like this. I want to know the position of this tip with respect to this. Now, this substrate or part or anything can be of any dimension, right? Consider this is this much substrate. I had this much substrate. Robot doesn't know what is being put here. Robot doesn't know, okay? But we know. So for our conscience, we know that this point has to be taken care of so that this point doesn't strike. So we have to always, in welding, we have to keep a safe distance, which is known as the standoff distance. Right? So we basically move the torch somewhere here. And the nozzle is also inside this only, okay? And this distance is known as the standoff distance. And now your machine knows that this is my starting point. And specifically, if you change this tool, so this is this much length, Consider I was using a smaller tool, right? So then also it will basically know, but the machine doesn't know what tool is placed on this. What is the constant thing that knows? This end effector XYZ knows. Consider that this is the tool. I am taking this end effector, the torch is moving downwards, the end effector is also coming like this. This is your torch and this is the end effector. This is called as end effector. Okay, end effector is like this. Okay, so now the end effector basically doesn't know this position, or the robot doesn't know this position. This position could happen like this also. It doesn't care. The end effector is like this, and the end effector's XYZ relative to this point is basically what is defining the coordinates. This is fixed. This can't be fixed. We change the tool, it is changed. But this is for our reference, because we don't want our setup to strike, or we want to keep a safe distance or whatever.
Fix that. How do we fix the starter distance? What's
This
the
distance?
mechanism to fix that distance?
Yeah, we just will move the robot and using all this
So
programming.
you're
you move
moving the
robot.
arm and fixing physically. There is no programming for that.
It is not okay. Backend programming is there, but when you are conducting like motion, it is known as jogging. So you jog the robot to that position. So you are using the motors. See, every joint has a motor.
Accuracy, how is it?
Accuracy. That is something I need to check. So it depends upon the robot's. Yeah, that is a good question. Can you go to Sujata? She operates this machine.
Similar question I would be top frequency is looking. So there will be
Explain, ma'am.
Yeah, but she's asking accuracy.
Yeah.
What accuracy of this machine? Like by what accuracy does it do? Point how much?
Meaning least distance.
Huh? Least distance basically what you can go.
Okay, like the standard distance.
She's asking the accuracy.
Accuracy is good position.
Accuracy of this positioning the nozzle to the substrate and the component what we manufacture.
If we have
How
to print the
accurate?
10 mm specimen, we have to print the code is the code we have the input 10 mm. So what will the that is what you are asking, right?
मैंने बोला कि मैं कंप्लीट 6 mm स्टैंडर्ड डिस्टेंस वो एक्चुअली कितना देता है बट that you have to check.
लेकिन यहाँ पे एटलीस्ट 12 mm डिफरेंस रखने से
No, that is end of distance. They are asking about the accuracy. You say 6 mm precision. Yes. We need to check. Mm is too much. It will be micron. It isn't micron. Okay. If VMC gives in 0 point something mm, then of course. So what is point? Yeah. We'll check and get back.
Yeah, yeah, no. You're explaining me the coordinates of the nozzle. You're
Asking
studying.
how do you take the coordinates and they have different setup. Basically changing every time. So how
With the tool changing, you are saying that how okay. So for example, okay. Now because there is a welding tool only. Okay. So I want that this is to be my starting point. Understand? So I will basically be jogging the robot in first 3 axes, X, Y, Z. It comes majorly to this point, and then I need to do some rotations that I do because the robot is like this. Now it has to come like this. The robot has to come like this. So this 4th, 5th, and 6th axis will also rotate. We'll bring it close to that. Now how that closeness we check mostly is we use a paper. Generally, a paper distance. Basically, we will keep a paper and we'll try to strike. Then we'll move this by maybe 0.001 changes we make.